Jason Saied from Rutgers University talk about combinatorial formula for SSV polynomials.
Thanks so much for having me, and thanks everyone for coming. So I'm going to spend most of the talk telling you about alcove walks, and then at the end, I'll tell you what SSV polynomials are and point out this connection. But for now, you should think about them as some very general polynomials that generalize things like Mcdonald polynomials and Schur polynomials. So what we're going to do is we're going to first fix some notation. So everything I say really corresponds to a root system. But today I'm just going to talk about type A, so I'll be as concrete as possible. So we'll fix positive integers n and r, and v will just be our Euclidean space. And then for numbers I and j, oh, there should be a j in here. For numbers I and j, and any number t that's divisible by the n that we fixed, we can define a hyperplane depending on these things. It's just the space where vi minus vj equals t. So it's these planes that cut up the space into pieces. And the n alcoves are what you get when you throw away all the hyperplanes. So you remove all the hyperplanes where t is divisible by n, and you cut up the space into these pieces. So let's look at a picture to make sense of this. So what we'll do is we'll look at r being 3 and n being 1. And this would be a three-dimensional picture, so I'm going to project it onto a two-dimensional subspace, which has all the interesting stuff going on. So what happens is we have this green hyperplane, which is the H120 hyperplane. And then similarly, we have, the orange and the blue and the red, etc. And what you can see is that when I change the superscript, what I'm really doing is I'm just translating the hyperplane up or down by one unit, or maybe side to side. Oh, and the alcoves, so here are the one alcoves. They're just these pink triangles. And so I'm going to be using this picture throughout the talk. Alcoves are just little triangles. And I want to introduce some notation. So I have a group of reflections coming from these hyperplanes. So Si upper n is the reflection through the Hi I plus 1 hyperplane. And S0n is the reflection through the H1r upper 1. So what's happening here is when I talk about the SIs, really, I mean the reflections around this one triangle. So the green one is one of the walls, the orange is another, and the blue is a third. And so the SIs are generating all of the reflections through all of these lines, but you can get them just by looking at what happens at the one triangle. I see a question in the chat about the bold lines. So that is sort of telling me about the S0 action, but I can explain that more later. But so if I try to act with the S0 on the right, it'll be coming from the bold lines rather than from this blue line. I can explain more at the end. But okay, so we're interested in this group, Wn, the n-affine Weyl group. And it's generated by, like I said, these reflections around a single alcove. So another example, n isn't always 1, although my pictures will typically have n be 1. But here n is 3. And so we only look at the orange hyperplanes. So all the black lines are just hyperplanes, but the orange ones are the ones that are interesting to us. And now our alcoves are bigger. So this pink triangle is a single alcove. It's just one connected component when I cut out all the orange stuff. And the only thing that's different in the three cases, everything is stretched out. So here I look at the 0 and the 3 and the -3, and I ignore like 1 and 2. So Wn is clearly isomorphic to W1, but it's useful to make this distinction because we want them acting at the same time. And so I'm going to define the notation A upper n to be what I call the fundamental alcove. And in the picture, it's just the pink one I highlighted above in both pictures. It's the alcove of all the elements whose entries are decreasing, and the greatest difference is less than n. But really, you should just think of this pink triangle. And it's interesting because it's a fundamental domain for the WN action on the alcoves. So if I take all these reflections, I can take any alcove to this alcove, and actually in exactly one way. And using this, we can identify elements of the N affine Weyl group with alcoves. So in this picture, I've written down a bunch of alcoves and the corresponding Weyl group elements. So here, this one, that's A1. And then, if you reflect over S1, then you're here, etc. So we can label the whole plane and all the alcoves with Weyl group elements. And I'll often be lazy and omit the upper one. So that's what I mean by SI is SI upper one. Any questions so far? Okay. So now I can tell you what an N alcove walk is. So they're just sequences of N alcoves. And I want them to start at the fundamental alcove. And in each step, either I do nothing, or I go to an adjacent alcove. I reflect over one of the walls of my current alcove. And we have a technical condition for an alcove walk called a type. And the type comes from some element in the Weyl group. What you do is you write that element as a reduced expression, so a product of the generators in some shortest possible way. And then the alcove walk has type W if when you do what I call a crossing, when you actually do something non-trivial, the thing that you multiply by comes from the reduced expression for W in a predictable way. If you haven't written this out, it might not be clear to you that this thing should actually be adjacent to AK minus 1, but it is. And so I'm going to be interested if I fix some W in all the alcove walks of a given type. So let's draw this out with a picture. Let's look at one alcove walks of type corresponding to this Weyl group element, S0, S1, S2, S0. So what I could do is in each step, I could choose to do a crossing. So I start at the identity, I start at 1, and then I do S0 on the right. And that brings me from here to here. Then I do S1 on the right, which takes me here. Then I do S2, and so on. And then S0. And so this is some sequence of alcoves that carries me through the plane. And I call the endpoint of this alcove walk, whichever alcove you stopped in. So here I got to W. But I don't have to cross every time. So here's a different example of an alcove walk. Same W. But now what I'm going to do is I'm going to choose not to use S0. I'm going to do what's called a fold there. And the way you visualize this in the picture is I go to the hyperplane I should have crossed and then turn around. So I don't actually do anything. But then for the next step, I'm going to choose to cross at S1. So that means I go into this hyperplane, this alcove. Then I'm going to fold at S2. So I go to where I wanted to, but then change my mind. And then cross at S0. So by some sequence of foldings and crossings determined by the Weyl group element I started with, I get some path across the plane from alcove to alcove. And here the endpoint is S1, S0. Okay. So that's a brief primer on alcove walks. Now I want to very quickly tell you about the kind of polynomials that we are interested in. I'm going to be very sketchy here. So first, let's let G be the group GL and C. So just all invertible n by n complex matrices. And I want to remind you that a representation of a group is just a map from that group into the endomorphisms of some vector space. So rho sends G to GL of U. And really, I study representation theory and the combinatorics associated with that. And the point is that if we have a sufficiently nice representation of this group, it's determined by what's called the character. So it's a function on the group. What you do is you take the group element, you map it into the endomorphisms of some vector space, and that's a linear map, so you can take the trace. So now for every group element, you get a number. And it turns out that you don't even need the whole character to determine the representation. It's actually determined just by the value of the character on diagonal matrices. And so this polynomial here, it's a polynomial in the numbers x1 to xn, is called the Schur polynomial. I'm lying slightly. Technically, you want to require that the representation is irreducible, but this is good enough. But so the point is, by understanding the combinatorics of these things I'm calling Schur polynomials, I can learn about the representation theory of the group GLN. And there are many instances like this out there. I'm not just interested in Schur polynomials. So let me sort of give you a hierarchy without really defining anything of a bunch of polynomials that come up. So we talked about Schur polynomials, and these are, another way to get them is as what are called zonal spherical functions of the pair GLRC and UR. So really you're looking at a certain representation and you're finding a very nice basis for it. And these give you Schur polynomials, but also you can do such things for other pairs of groups. But there's all these levels of generality where there are these other families that sort of recover all of this stuff at the same time. So Jack polynomials, they depend on a parameter alpha. And when alpha is specialized to different numbers, you recover all of these different things. But also there's various things. So these de Major characters tell us about representations of affine Lie algebras, blah, blah, blah. But what people in my field like to study are Mcdonald polynomials, because they very nicely generalize all of this stuff I'm talking about. So they have some parameters. There are these parameters Q and T, and when Q and T are specific numbers, they recover all of the stuff above. But I decided to take it one step further, or really my advisor did. They discovered a family that I call SSV polynomials. And these generalize Mcdonald polynomials, but also these other things known as metaplectic Iwahori-Whittaker functions. So these Whittaker functions, they have to do not with GLN, but with certain covering groups of GLN that are not algebraic groups. So there's these interesting number theoretic objects that until now were not part of the family of Mcdonald polynomial stuff. But now we can learn something about Whittaker functions by studying these SSV polynomials. And so I want to tell you a little bit about those. Okay, so in 2019, these polynomials were found by my advisor, Siddhartha Sahi, and his collaborators, Jasper Stokman and Vijay Venkateshwaran. And they're polynomials E mu, depending on the integer tuple mu and a positive integer n, and a bunch of parameters that don't matter for now. But when n is 1, you get the thing that we understand better, the Mcdonald polynomials. Another example, so that you can all say you know some SSV polynomials. If lambda lives in our fundamental alcove, then actually E lambda is just a monomial. It's just x to the lambda. So there are some easy examples. But the rest are more complicated, but not too bad because they satisfy a recursion. So there are these operators tau I that when you do tau I on E mu, you get E sin mu. So it knows about the n, and it permutes the entries of mu according to sin. So because an is a fundamental domain for the action on all the alcoves, you can actually get all SSV polynomials using this recursion. So then what I did was explicitly solve this recursion, following what Ram and Yip did in the case of Mcdonald polynomials. And we get the following formula. So you have some integer tuple mu, and you can find a lambda in the fundamental alcove and a w that takes lambda to mu. And then the formula for E mu is just the sum over alcove walks of type W, same W, of some coefficients that I'm not going to give here, times X, where the power of X depends on the endpoint of the alcove walk. So by studying all of these alcove walks, we have very good control over what's happening. And at the end, I'll flash the formula for the coefficients. I know it very explicitly, but it's just gross. Or at least if you don't know the notation, it's gross. Okay, so I know I'm about out of time. So let me finish with some quick corollaries of this. So the first result is that if we study which powers of X appear here, they actually satisfy some sort of triangularity. So you can define a new ordering on the space of integer tuples. It's technically new, I think, but also it's not very, it's obviously related to things people understood. But you get some sort of triangularity where E mu is X to the mu plus lower terms. And further, all of the coefficients are actually non-zero. So I know exactly which powers appear here. You can also relate E mu as n varies. So if you have m dividing n, then as m gets smaller, you have fewer, as n gets larger, you have fewer powers. So in particular, E mu upper 1, the Mcdonald polynomial, has the most powers, and everything else has less. And also with the explicit knowledge of the coefficients, we get very simple formulas for the limits when the parameter q goes to 0 or infinity. And the reason why we care about this, I haven't really even talked about the parameters, is that this is how you relate to these metaplectic Whittaker functions. So what this formula does is it gives me a new way to understand those Whittaker functions in terms of alcove walks. And I'll stop there. Just to be slightly intimidating, I'll put the theorem up at the end. Thanks for your attention.
Let's thank the speaker. Does anybody have any questions?
I have a question.
Okay.
So you have this nice formula. Do you have a sense of like where your future work will go from this?
Yeah. So thanks for that question, by the way. So with the less general version of this that worked for Mcdonald polynomials, Yip, one of the people who proved the formula, they had a nice result for what they're called Littlewood-Richardson coefficients. So if you take two of these Mcdonald polynomials and multiply them, how do you expand them in terms of other Mcdonald polynomials? And so I'm currently doing that. I have most of it down already. I'm writing up the details for these new SSV polynomials. So that's the first application I'm looking at.
Cool, thank you.
So do you have like combinatorial representation for this Littlewood-Richardson coefficient you're looking at?
Yeah, so I mean, in the end, they will also be described by certain alcove walks. Okay. You'll have to, so I didn't talk about this in the talk, but the alcove walks, each fold has what's called like a positive and a negative sign. And this information helps us track more of what's going on with these coefficients. But so for the Littlewood-Richardson rule, I have to like add more decorations. Like I have to care not just about folds, but like, you know, in what situation is the fold happening? But once I add suitable decorations, then the coefficients are also given in terms of certain alcove walks.
Well, let's thank the speaker again. Thank you for the talk.